Start recording now. Okay. So up to the last class, so whatever we have done, I have just already mentioned in my first class that this is a new chemistry, may not be properly familiar to you. So we have just discussed that how the coordination complexes formed, and then they deduce the structures of the coordination complexes. Then we have just seen that different sorts of ligands. So ligand may be containing the hetero means the donor atom, either neutral or anionic charge will be there. So so either neutral or anionic ligands. Okay. So that much we have just done yet, and the different the classification of the ligands, like the monodentate, bidentate, tridentate, tetradentate, pentadentate, hexadentate, means depending on how many coordination site surrounding a metal center the ligand donor atoms can occupy. Depending on that, it will be said. And then another important point, whatever we have discussed in my last class, that was that whether a multidentate ligand may be utilized like or may be called a chelating ligand or not. If all the ligand donor atoms are attached to the metal center, and if it forms the 5 or 6 member ring, so those are the stable one, then it will be said the chelate complex, okay, of that particular ligand. So if it forms like ethylene diamine, I had given one example, ethylene diamine. So if you just both the nitrogen donor atoms of the amine groups coordinate to the same metal center, then it is going to form a 5-member ring. 5-member and 6-member ring formations are the most stable one. So if you want to design a new ligand and just to check how it will behave like the complexation with different metal ions, you have to check that if it coordinates via its donor atoms, then whether it forms the 5 or 6-member ring. So those are the most stable rings. If below the 5-member, means like the 4-member, 3-member ring, so those are not stable, and as well as like the higher member rings, like above the 6-member ring, those are also not stable. Then we have seen that based on the ligand donor atoms, so whether it is present more than one donor atoms, and then it can coordinate like via either one of its donor atom, then it will be said an ambidentate ligand. And also we just discussed the another ligand which is known as EDTA. EDTA is ethylene diamine tetraacetate anion. It may act as a pentadentate ligand, it may act as an hexadentate ligand or a tetradentate ligand. That means it is flexible to coordinate to a metal center to provide a certain number of like either 4, 5 or 6 coordination sites occupation surrounding a metal center, and that's why it is known as the flexidentate ligand. So the previous one was based on how many donor means like the coordination sites the donor atom of a particular ligand can accommodate, okay, or will be accommodated surrounding the metal center. It will be said mono, bi, tri, tetra, penta, hexa dentate ligand. And other classifications are like the ambidentate ligand, flexidentate ligand, and then another term you can just hear, that is the homoleptic compound and heteroleptic compounds. Okay. So what does the homoleptic compound mean? Homoleptic compounds, here you can just check this one, homoleptic compound. Homoleptic compound means if a compound has the same ligands are there surrounding itself, then it will be said a homoleptic compound. Means like here in case of this one, cobalt and then 6 ammonia molecules are surrounded to that cobalt center. So 6 ammonia molecules. So ammonia molecules, it is coordinated via its nitrogen donor atoms. Okay. But if suppose the ligand is all are nitrogen donors, 6 nitrogen donors are there, but those 6 nitrogen donors will come, let us say 4 from the ammonia groups and 2 from the pyridine groups, pyridine nitrogen atoms, then it will not be said like a homoleptic compound. So homoleptic compound means your all the ligands which are coordinated to the metal center are same. But if it is not same, then it will be said a heteroleptic compound. And there are plenty of examples of the heteroleptic compounds. So like here you can just see in this case, okay, NO2 and NH3, here NCS and NH3, here Cl and PPH3 means phosphorus donor atom, phosphorus is the lone pair of electron, and here chlorine or chloride and the ammonia groups are there. So these complexes will be said the heteroleptic compounds. Okay. So then I am coming to the naming of the different metal complexes. So there must be one like the IUPAC name. Okay, if I just means give that name over the whole world, people will understand what compound we are talking about. So the naming of the means the coordination complexes are very important, and how can you name those ones? So writing and the naming of the complex compound will be different. So writing a complex compound, so there are different things, okay, depending on the coordinations number, how the coordinations geometry a surround metal center can adapt. So that has been shown here. If it is trigonal planar or tetrahedral, square planar, trigonal bipyramidal or square pyramidal in case of 5 coordination number and hexacoordination number. So these are already have been done. Now I am just coming to this one, that is the naming of the metal complexes or coordination complexes, I should better say. So plenty of examples are there, but we will just start from the very beginning. Like let us consider here. So how can you write down a coordination complex formula? So coordination complex formula, first of all, you have to write down the cation. So this is the cationic part. So this is the cationic part, sodium, and then the coordination complex here. So writing down the coordination complex, first you have to put the metal one. Which metal is there? So here platinum is there, and then the anionic ligands. So anionic ligands will come first, and then after that the neutral ligands. And in both cases, if you have several number of anionic ligands or the neutral ligands, it will follow the alphabetical order. Like in this case, you see bromide, chloride, and nitro groups are there, which are negatively charged. So the negatively charged anionic donor centers containing ligands will come first, and after that the neutral one will come. So here bromo and then chloro, so B, C, and then nitro, N. So alphabetical order it is just going to maintain. So this is as simple as that. So you have to write down first the metal, and then the anionic ligands, and after that the neutral ligands. And anionic ligands and neutral ligands will follow the alphabetical order. So this is as simple as that. Now I am just coming, how can you name this one? So naming this, the coordination complexes will be a little bit different. But before that one, we have to just know about how the name of the ligands will be. We can just mention from a formula of a coordination complex. So all these things are here. So here you see the naming a coordination complex does not follow the sequence used in writing its formula. For instance, okay, metal should come at last in this one. Atom symbol appears last in the naming. So first you have to name all the ligands. So all the ligands name first, and irrespective of their charges, it does not matter whether it contains a negatively charged donor atoms or it is a neutral ligand, you have to follow the alphabetical order for naming a coordination complex. So first name all the like the ligands, and after that your metal will come. So whenever you are just naming, alphabetical order you have to follow. It is irrespective of the charge of the donor atoms of the ligands. So that means it might be negatively charged, or it might be positively charged, or it might be neutral, but you have to follow the alphabetical order. Then another questions might come, like suppose 3 or 4 different types of donor atoms or the ligands are attached to a metal center. Then we are going to follow the alphabetical order, there will be no problem. But suppose one of the ligand has different number than the others. So you have to mention that one too. How can you mention that one? For the case of simple ligands like the chloride, bromide, or simply chloro, bromo, iodo. So this type of ligands, okay, we can just utilize bi, tri, tetra in order to indicate 2, 3, 4 penta, hexa, 5, 6. Okay, numbers are present. Okay, surrounding the metal center. But if it is polysyllabic ligands means like ethylene diamine, let us say, okay, or maybe another ligand, trispirazolyl borate or something. There are many other ligands are there. So those are polysyllabic ligands. Some organic moieties are there, and then the heteroatoms are embedded over there, and it is acting like a ligand. In those cases, in order to indicate how many numbers of those ligands are there, like the bipyridyl, phenanthroline. So it will be said then bis bipyridyl or bis phenanthroline. That means 2 phenanthroline ligands or 2 bipyridyl ligands are attached. Okay. So the bis, tris, tetrakis, pentakis, and hexakis. So these will be used in order to indicate how many number of a particular ligand which is polysyllabic in nature will be used. But in case of the simple ligands, we can use bi, tri, tetra, penta, hexa, like that. Okay, so these are the things. Now we have to know that in case of the name for the naming the ligands, okay, so ligands may be neutral or may be anionic in nature. If it is anionic in nature, so this will be said fluoride. Okay, so fluoride, so one E is there, so the last E will be replaced by O. Okay, so fluorido or fluoro, you can say chlorido or chloro, nitrito or, okay, so this is the nitrite anion, so nitrite. Okay, so E will be there, so E will be replaced by O. Okay, so this is the, so this one final E is replaced by O, giving iodo, ito, ato, like sulfato, nitrato. So nitrate is an anion, so E is there, so it will be said nitrato. Okay, so ato or means that the E will be replaced by O, so that will indicate then your negatively charged, okay, ligand centers are there over in the complex. Okay, thiosulfato. So this kind. Now the other ligands. So these are the simple ligands you see. So usual name is fluoride. You can write down fluoro or sometimes fluorido. Okay, and here you can just see this one. So like in case of hydride, so hydride, it can be said like a hydrido or hydro. Okay, in case of the oxide, it can be said oxido or oxo. In case of hydroxide, it can be said hydroxo or hydroxido. Okay, azide, azido, cyano. Okay, so these are the name of the ligands we have to utilize while naming a coordination complex. And you have to know that which, you know, abbreviations, because as you know that alphabetical order of the ligand names should come first. Okay, alphabetical order we have to follow. Then you must know that which ligand names we are just utilize. Like in case of the NO, we will utilize nitrosyl. So N will come, here is also N. But you have to remember here ammonia. So amine, A is there, no problem. But in case of the water, you see it is W. But instead of water, while naming the water ligand, you have to utilize aquo. So A will come, okay, first. So as we are just going to maintain the alphabetical order, so instead of water, you have to consider aqua. Okay, so nitride, nitrido, all other things are there. Carbonyl, carbon monoxide, carbonyl. So all others are fine. Okay, so naming the ligands, then nitrosyls, and water will be aqua, ammonia will be amine, and then, you know, the CO will be carbon monoxide or carbonyl. We have to name in this way. Now I am just coming, okay, another problem will arise. So the first one was alphabetical order we are going to follow. Then we have to know irrespective of the charges. Okay, then we have to know how many number of a particular ligands are there. In order to say that one, we can just utilize bi, tri, tetra or bis, tetrakis, pentakis, hexakis, like, you know, polysyllabic in case of polysyllabic ligand or the simple ligand. So that is done. Now suppose there is a ligand, ambidentate ligand. So ambidentate ligand has more than one donor atom. So you do not know through which it will be coordinated to the metal center. Like suppose if you have the NCS, thiocyanate, NCS, okay, or SCN. So it may coordinate via this atom or it may coordinate via that atom. So NO2, N double bond O, O minus, and this O minus will be just, if, okay, means resonance stabilized. So better you can just write down NOO and then here 1 minus charge. So it may coordinate via this, or it may coordinate via one or both of the means oxygen atom to the metal center. So we have to mention now through which it is coordinated to the metal center. So this is the third point you have to remember. Then after naming that particular ligand, you have to write down like here kappa ON or kappa S, thiocyanato kappa S, thiocyanato kappa N. So that means it will indicate, sometimes you can see in the formula either S or the N are italics in nature, but italics in nature we cannot write down, you know, on a piece of paper. So it will be better to write down like kappa N or kappa S in order to mention through which it is coordinated to the metal center. So naming the ambidentate ligand, whatever I have described right now. So thiocyanato kappa S. nitrito N or nitrito O. It may coordinate via nitrogen or the oxygen atoms. And then you have to remember, after all the name of the ligands, the metal will come into the picture. Now you can simply write down the metal, and then in the parenthesis, means within a first bracket, the oxidation state of the metal center. But if as a whole your complex entity is negatively charged, then you have to write down one ATE, 8, to that metal ion. Like I am suppose first one, whatever example I had given. So in this case, okay, in this case you see this complex entity, it is ultimately or overall one negative charge is there. So you can just think of it is sodium plus, and then you have this one, the platinum, okay, Br, Cl, NO2, then NH3, and then ultimately one negative charge is there. If your complex entity is negatively charged, then after the name of the means like the metal ion, like here platinum, so you have to write down platinate, okay, platinate. If it is iron, then it will be ferrate. Cobaltate means cobalt, so it will be cobaltate. So in this way, now I am just coming to different names, and then it will be easily understandable to you, and you can just score few marks in your either class assessment or some main exam as well. So let us first start from the first one. So cobalt. So cobalt, and then this is the nitro, and this is the amine group. Okay, so nitro and amine are there. So whenever you are writing down the formula, first you are writing the metal center, and then the negatively charged ligands, and then the neutral ligands are coming. But whenever we are naming, it does not matter. We have to consider the alphabetical order of the neutral as well as the the anionic charged ligands are there. So the nitro, N, and amine. So amine will come first. So we have to write down then the amine. But amine, you see here, 3 number of ammonia molecules are attached to the metal center. So you have to mention this one. As ammonia, this is a simple ligand, so you can just utilize tri. So this is a triamine, okay, and there will be no space in between the name of the ligands. Triamine, and then here again tri, because the 3 nitrito was there, nitrito kappa N, okay. So tri nitrito kappa N. Kappa N indicates that this is an ambidentate ligand, nitro group, so it is coordinated via its nitrogen donor atom. And then one hyphen, then cobalt 3, because this is neutral. So this is either neutral, or in case of the positively charged, okay, complex entity, you have to name simply the metal name, and after that within the parenthesis its oxidation state. So oxidation state you have to calculate here. 3 nitro groups are there. 1 nitro group has 1 negative charge. So 3 nitro group, 3 negative charge. Definitely, and ammonia molecules are neutral in nature. So cobalt will be plus 3 oxidation state. There is no question about this one. Here, let us see. So this will be then the pentamine, and then azido. Azido means, so this azide group, okay, azide group N3, and this is negatively charged. In order to indicate the negatively charged donor atoms, you have to utilize, instead of E, azide, you have to write down O. So azide, instead of E, you have to replace E by O. Okay, so azido, and then cobalt 3, and after that one, the anion name will come. So first of all, you have to name the cationic part. The cationic part may be either the complex entity, or maybe a simple cation, like in the first one, that was sodium. So you have to write down first the cation name. So that was sodium, and then you just mention the complex entity's name. Here you see here that anion is a simple anion, but your complex entity is a cation. So you have to first name the cation. So pentamine, azido, cobalt 3, and then sulfate will come. So these are the examples. So now there are other examples where both the complex entities, the cation and anions are there. In this case, you see cobalt, hexamine, and in this case, hexacyano. So hexacyano, if you just consider this one is 3 oxidation state, so ultimately this will be 3 negative charge, and this one neutral, and if you have the cobalt in 3 oxidation state, then it will be +3. Okay, so electrical neutrality will be will occur in this way. So we have to name first the cationic part. So cationic part is then hexaamine cobalt 3. Okay, so this is the cation. And then what is the anion? Hexacyano, because cyano Cn minus. So this is not cyanide, cyanido or cyano, you can write down. And then you cannot write down here now chromium and then 3. Chromium you could have write down whenever it was either neutral or positively charged complex entity. But in this case, we have seen this is a negatively charged complex entity. Okay, so because of this reason, you have to write down chromate, ATE. So this will come ATE, and then the oxidation state of the metal center +3. Okay, so this is as simple as that, and plenty of examples are cited over here. Another example, let us say, so here several different sorts of ligands are there, and as well as the same ligand which is present as a counter anion. So whenever you are naming a counter anion, so that is done here. But other entity, the complex entity, so you have to first observe that which are, different sorts of ligands are there and their alphabetical order. So this is the chloro, this is nitro, I think. So this one will be like here. Okay, so nitro and then amine. So amine will come obviously first. And how many number of ammonia molecules are attached? 4. So it will be tetramine. Okay, so tetramine, and then chloro will come. So chloro. There will be no space in between the naming the ligands. And then nitrito, kappa N. Nitrito, as it is ambidentate ligand, it is coordinated via its nitrogen donor atom. So kappa N, and then hyphen cobalt 3. So this is the name of the cationic part. So this one is the name of the cation, and then the anion name will be here. So first the cation name, and then the anion name. Okay. So and another example I am just going to tell you. Here it is polysyllabic ligand. You see here ethylene diamine or bipyridine. These are polysyllabic ligand. But still here bipyridine bis ethylene diamine cobalt 3 ion. Bipyridine bis ethylene diamine cobalt 3 plus, either in this way or that way. I will.
Sir,
yes.
Sir, why in bipyridine bis is not used? Because that is also a bidentate ligand, no, sir? Because or not?
Bipyridine is very common. Okay. Bispyridine also you can say. Bispyridine also you can say. Okay. There are other examples as well where bispyridine complex will also be written down. But pyridine is very common. Okay, ethylene diamine is also very common, but still it will be written like it has been a designed ligand. Some other moieties are there. So why it's not said? Okay, means you can have some examples of where bispyridine will also be said. Okay, there are other examples. I don't know why it's not mentioning here, but this is only one book. Okay, so bispyridine you can just write down bispyridine bis ethylene diamine. Okay, so bispyridine complex is also known. So that is the thing. So here sodium and then tetracarbonyl cobaltate, and then 1 minus charge is there. It's written. You see there is the variation. Okay, here cobaltate, and then it just mention the ultimate charge of that whole compound here. But if you just try to write down again here also, you see here cobalt is -1 charge. Okay, so you can write down in Roman form. Okay, so means cobalt -1. Okay, so bromo bis ethylene diamine, here bromo and then bis ethylene diamine thiocyanato kappa N and then cobalt 3. You can write down in this way, or the other way is bromo bis ethylene diamine. I will follow this one. Okay, this is simpler than the other. And then thiocyanato kappa N cobalt 1 plus. So cobalt is in here 1 plus charge. No. Okay. So it is the charge of the whole entity. So this one. Okay. So there is another.
Iron should be used now in first one, in 11th example, cobalt iron, because it has a charge.
Yeah. So either you can mention one of this one. So this name we are just going to prefer because this will tell you the oxidation state of the metal center. But in the last one, this one, okay, we are just mentioning the overall charge of that complex entity. That's why I will prefer this one, but not that one. Okay, but you can write down in this way too. That's why it's written. So we are that's why okay we are just going to follow only one rule. So that is this one. So if it is, so you have to remember one thing, whether it is ultimately negatively charged. Here ultimately not negatively charged overall, so it will not be cobaltate. If it is positive or neutral, then it will be simple metal name cobalt and then mention its oxidation state, or cobaltate then mention its oxidation state. Okay. So here also the same thing, it will be said cobalt, not the cobaltate. But here, this example, see, so this is the cation. So we are going to name as cobalt, and then what is the oxidation state? Cobalt 3. But in this case, as it is as a whole, okay, if zinc is in the +2 oxidation state, let us say OH minus, so this will be ultimately 2 minus charge, and this should be then the 2 positive charge. Okay. So 2 positive charge will be there. So this is the cobalt 3 tetrahydrox. Again here some mistakes are there. Tetrahydroxozincate, tetrahydroxozincate. So zinc is in the +2 oxidation state. So this will be 2 minus. How come then it will be sulfato? Then either it should be HSO4, not this one, hydrosulfato. Is it not? Hydrogen sulfate. Okay, HSO4 then it should be. So these are the different, I mean, in books, whenever they have written down, there are some mistakes. But if it is sulfate, so it is 2. It is 2 minus. Okay, sulfate is 2 minus. If cobalt is in the +3 oxidation state, then it will be +1 charge, not the +2 charge. Then how come it can be electrically neutral? So this is not the right one. So that means if it is cobalt 3, then definitely it should be this ligand. Okay, one is protonated. So you can find out, little bit mistake here and there that I have not checked very carefully, but now I am just checking with you. So dichloro, this is fine. Dichloro, bisethylene diamine, cobalt 3, and then nitrate. This one, see. So here you have to write down ferrate and +3 oxidation state. If this is +3 oxidation state, then it will be ultimately 3 negative charge. So ferrate will come. But in this one, this will be 3 plus charge. Then 3 plus charge. So CO3, Na2, CO3. CO3 is 2 minus. Again, I do not note it. Carbonato. Is it not? I have to check this one. Okay. So this one is carbonate. So carbonato. So CO3 2 minus. If it is cobalt 3, then how come the charge balance will occur? I have not checked these complexes. So this is the tetramine, then carbonato, cobalt 3. So this will be then 1 plus charge. Is it? Oh, okay. Yeah, 1 plus charge, and then whole 3 is there. So this is fine. 1 plus charge. Okay, then whole 3 is there. So plus 1 charge, and then whole 3. So this is going to maintain. So this is fine. So tetramine, carbonato, cobalt 3, hexacyanoferrate. Okay. So let us see the previous one then. Then previous one should be, then it is 2 minus. So 1 plus. So this will be 2, I think. Okay. That will be 2. So then it will be electrically neutral. Okay. And sometimes whatever the students usually did some mistake naming this one. This will be the azide. Remember, if 3 is subscript of N and then minus, this is the azide ion. Okay. But so azido you have to name. Okay. But if you have the N and then 3 minus, so this is the superscript. So this is known as nitride. Okay. So it will be said nitrido. This one, this will be said oxo. Okay. So O is 2 minus charge. Then fluoride is 1 minus charge. So there will be total 6 minus charge. So chromium must be then in 5 oxidation state. Then only it will electrically neutral, because this is potassium is 1 plus. So this will be first name the cation potassium, and then the anionic part. So anionic part, which ligands are there? Oxo and fluoro. So fluoro will come first, then the oxo. How many fluoro is there? 4. So this will be tetrafluoro, okay, up to this, and then oxo, okay, and then chromium. So chromate, because ultimately it is negatively charged, because potassium is there, so the complex entity is negative charge, so it will be chromate, ATE will be added, and after that the oxidation state of the metal center. Okay, so you have to remember these few things in order to name, name the coordination complexes. These are different sorts of coordination complexes are there. Is it okay for you? Or anywhere any confusions are there?
Okay, sir.
So one more thing, like here. So if I just simply give this one, so you will say potassium ferrocyanide, okay? We usually name in this way, but don't write down the name in this way, okay? Or sometimes lithium aluminium hydride, we write down lithium aluminium hydride, but this is not, we are not going to give you the marks. You have to name this compound's name according to the coordination complex name, okay? So here you see tetrapotassium or simply potassium. It does not matter whether you are writing tetrapotassium or potassium, okay? There are some flexibility naming the ligands, but ultimately it will give you the same name. And then hexacyanoferrate 2 or hexacyanoferrate 2, okay? So either tetrapotassium or potassium, or you can just write down the total, negative charge, how many it has been generated, this complex entity in this way, whatever I have mentioned just before this one, okay? So you have to name, so potassium ferrocyanide or potassium ferricyanide, you cannot write down in this way. So this will be said potassium ferrocyanide because iron is present in the +2 oxidation state. But if iron is present in +3 oxidation state, then it will be said potassium ferricyanide. At that time it will be K3FeCN6, potassium ferricyanide. But you cannot write down potassium ferricyanide or potassium ferrocyanide. You have to write down in this way in order to mention the ligands and how many number of those ligands are present in the complex entity, but not the other part of the entity. You can write down simply tetrapotassium or potassium. It does not matter. Okay. So this one, the lithium aluminum hydride, that example is also here. Here. Okay. So this is the lithium and then aluminum, and then 4 H's are there. So aluminum H4 minus. So this is one entity. Aluminium H3. So this is neutral. Another hydride group, because this is electron deficient. So AlH4 minus it can make. AlCl4 minus. AlCl3 releases the rigid knot. So the AlH4 minus, and then you have the lithium plus. So lithium 1 first you have to name, and then there should be a gap. So this is the cation. Then tetrahydrido or tetrahydro aluminate. Why aluminate? Because as a whole this one is a negative charge is there. Because of this reason you have to write down aluminate. And then what is the oxidation state? +3. If it is +3, then you require another plus, because you have 4 minus charge are there. So you have to just remember this one for naming the different complexes. So this one, this will be simply said hexafluorophosphate. Okay, hexafluorophosphate 5. So what is the oxidation state of phosphorus? So that will be said phosphate, or you can just mention the overall charge of that particular entity, complex entity. Either one way. I will prefer to mention this one because it will just give your knowledge regarding the oxidation state calculation. So those things are there, not simply the charge of that compound. So these are the things. So there are plenty of examples. So you are just here. So this is, you see, so one N is there. Sometimes azide you just write down like this way. O3 you just write down ozono or something like that. We have seen that students usually do some mistakes here over there. But always remember N. So here N is 3 minus charge, and one oxo is 2 minus charge, and those type of oxo are 3 in number. So this will be named like potassium, that is a simple cation one. Then osmium and this one, okay. So so this will be nitrogen N and oxygen O. So N will come first. So nitrido. So this is said nitrido, not the azido. Okay, remember this one, whatever I mentioned previously. And then oxo. Oxo means, so this entity will be said the oxo. How many number of oxo you have? 3 number. So it's written like this way. It does not, put inside the bracket and then 3 subscripts. Okay, it's written like simply O3, and O3 is the molecular formula of ozone. So sometimes, people do some mistakes. So trioxo. So 3 numbers are there, trioxo, and then osmate 1 minus, or you can write down what will be the oxidation state of osmium here. You just calculate this one. So oxygen 3, so 6 minus, then plus 3 minus, so total will be 9 minus, 1 potassium is there, so definitely your osmium will be plus 8 oxidation state. So this is the 8 oxidation state. You can write down potassium, nitrido, trioxo, osmate, and in 8 oxidation state. Okay. Then but there are some means like the bridging complexes are also there, but we are not including those the name of those coordination complexes. Simple coordination complexes name will be asked from you. So you do not have to remember the bridging complex coordination complexes. So that's all. Now I am just going to tell you 2 new things which does not cover in this notes or whatever we have sent. So those 2 things are inner metallic complexes. So what does the inner metallic complexes means? Inner metallic complexes, let me just show you this one. Okay. So in the last day I took the class of the G section. So inner metallic complexes. Inner metallic complexes means like the complexes where your ligand system must have neutral as well as anionic donor centers are there. So what will happen? That type of ligands can fulfill either fully or partially both the coordinations number as well as the charge of that complex. So if your coordination number and charge both are fulfilled fully, then it will be said first order inner metallic complex. Like here, this is known as the acetyl acetonate. So acetyl acetonate, if you have, this O minus is there, O minus will be delocalized over the whole system, and you can just write down this way. Because if you do the X-ray structure for a single bond, you expect 1.5 angstrom, bond length carbon oxygen. And in this case, carbon double bond O, this will be around 1.30 angstrom, just like the benzene ring. Benzene ring, like you have 3 double bonds, alternate double bonds are there. So Kekule provided the structure. You can write down this one, or you can write down the other bonds like here. This is the structure. Okay. So if you just move these bonds like here, then you can write down that one. So this is called the resonating structure. How do you know the resonating structures are there? Experimentally, if you solve the X-ray structure of any crystal, so where either the benzene ring or the pyridine ring or some other rings are attached to this one, you are going to observe all the carbon-carbon distances are almost similar. Very little bit differences on the 3rd digit will be there, or the 2nd digit will be there, but definitely not on the 1st digit. Okay. So this indicates, so you are going to get 1.39 to 1.40. Okay. So this angstrom. So in all bond distances. So if these pi electrons were not delocalized, localized on these 2 carbon atoms, so definitely you are going to observe, let us say this is C1, this is C2, this is C3, C4, C5, and you are observing the bond distances. So C1, C2 distance should be then like the double bond distance like 1.30, and you can expect C2, C3, so that should be 1.50. Okay, but we are not going to observe these distances because the pi electrons are delocalized over the all fixed number of carbon atoms, and we are going to observe the all distances almost equal 1.39 to 1.40 angstrom. Okay, so this indicates that the resonating structures are there. None of the resonating structures are either one of the resonating structures are actually localized, okay, in the structure. So that's the case. So in this case, there are two donor centers are there, acetyl acetonato. One of the donor center is negatively charged. You can just write down the resonating structure because there are adjacent double bonds are there, adjacent conjugated double bonds are there. So the electron can be delocalized over all the whole system. So you can write down like this. So if you have 3 number of acetyl acetonate and a metal complex, if it forms, like metal is cobalt acetyl acetonate, manganese acetyl acetonate 3 number, vanadium also sometimes you can make the complexes vanadium, oxo-vanadium, and 2 acetyl acetonate molecules are coordinated, so it will be square pyramidal in nature. So we are just going to consider this one and just to see whether its coordination number as well as the charge of the metal ion are fully satisfied by these ligands. If it is fully satisfied, so that type of complexes will be said inner metallic complexes of first order. So inner metallic complexes will be said either fully or partially satisfied by a ligand, okay, both the coordination number as well as the charge. So definitely your ligand system must have neutral as well as anionic donor center. If it is there, then it is going to definitely fulfill some of the coordinations number or few number of the coordinations number as well as the charge of the central metal atom. Okay, if it is fully satisfied, then it will be said inner metallic complex of first order, and if it is not fully satisfied, then it will be said inner metallic complex of the second order or the partially fulfilled. So here is the example, the same acetyl acetonate ligand. So one negative charge is there, and silicon complex, if it makes, you see here all the coordination number fully satisfied, okay, because this is hexacoordinated, fully satisfied. But the charge of the complex or charge of Mn plus is not fully satisfied. So this will be said like inner metallic complex of the second order. Okay, there is another one complex is there, so that is known as the inner metallic complex of the third order, and the particular examples I am going to give one here. This is known as the biguanide. So biguanide, if you deprotonate this proton 1 NH, so you can make a negative charge on this nitrogen atom, which will be delocalized onto the system, and it will act like a C2N5H6 and then 1 minus charge ligand. So this can make a copper complex which will be neutral in nature. So this will be said then the inner metallic complex of first order, because in this case copper is in the past +2 oxidation state. So copper, and then you have N donor, N donor. So N donor, and N donor is there. So one negative charge, here one negative charge, and here copper is in the +2 oxidation state. So both the coordination number in case of the square planar complex, both the coordination number as well as the charge of that metal ion has been fully satisfied by the presence of two ligands, okay, or the bis biguanide or the biguanide ligand. So this will be said inner metallic complex of the first order. Now if you simply protonate this inner metallic complex by putting some HCl, so your anionic donor atoms embedded on the ligand frame will get protonated to make C2N5. So this is C2N5H7. C2N5H7 is on the top one. Okay, so this one C2N5H7, where your proton is there. At that time, you require for the charge neutrality, you require 2 chloride anions, and those will be outside the complex entity. So you can just make one complex inner metallic first order, inner metallic complex of first order, that can be protonated somewhere on your ligand frame, so that it will go to a water soluble complex. So that will be said third order inner metallic complex. So this complex is water soluble, but if it is electrically neutral, that might not be soluble in water. It depends on whether you have other electronegative atoms are there and hydrogen atoms are there or not, so that with the water molecules it can form the hydrogen bond and it may go to the solution. But simple saying is that polar compound will get dissolved polar compound will get dissolved in polar solvent and non-polar compound in non-polar solvent. Okay, so in this case this is polar in nature, so 2Cl minus, so this will act like a bi-univalent electrolyte, so it may be soluble in water, but you can expect as it is electrically neutral, it might not be soluble in water, possibly not soluble in water. Okay, so you are making a water soluble complex just after protonating some negative charges present on the ligand system of a complex, then it will be said a third order inner metallic complex. So this complex will be named third order inner metallic complex, whatever complex you have formed. Okay, so simple other example. Yes.
So couldn't understand the second order one. How is it partially filled balances?
So second order silicon. So silicon, I'm just writing here. Okay, silicon, you have 6 coordination number. Okay, so let us say 1OO. This is one ligand, this is another ligand, and the other ligands. Okay, so these are the acetyl acetonetal, ACAC ligand, it will be said. Okay, so this one is ACAC ligand. So bidentate ligand. So the 6 coordinations number of the silicon are fully satisfied. So coordination number, this is known as the coordination number, fully satisfied. Okay, but the charge of the silicon is +4. Okay, so if it is +4, you have 3 negative charge, 1 negative, another negative, and another negative. So it will ultimately be positively charged. So 1 Cl minus you require in order for electrical neutrality. So this Cl is here. So its charge is not fully satisfied. Charge of the metal ion, Mn plus ion. Here Mn plus ion means silicon. Okay, that is not fully satisfied, but the coordination number is fully satisfied. So that will be either coordination number or the charge. If not fully satisfied, then it will be said the second order inner metallic complex. If both are fully satisfied, then it will be said first order inner metallic complex. But the third order inner metallic complex, you can say, if you can generate of the same ligand system after protonation, one will be soluble in water, okay, and the other is not soluble in water, and that is first order inner metallic complex, that will be said third order inner metallic complex. So these are the things. Okay, now sometimes you have heard about the organic sequestering agent, because in your practical class also there is a system, the idiochrome black tea and the total hardness of water. We are just going to discuss regarding that practical in the practical class, and just tell you at that time also regarding this organic sequestering agent, which will be said organic sequestering agent. Organic sequestering agent means it is an organic ligand which forms a metal chelate soluble in water. Okay, if it is soluble in water, then only that organic ligand will be said organic sequestering agent, and the metal ion will be said sequestered. But if it is not soluble, after making the complex, if it is not soluble in water, it will not be said organic sequestering agent, but a simply organic ligand. So a organic ligand will be said organic sequestering agent if it forms the complex with a metal ion which is soluble in water. Then only it will be said organic sequestering agent. Okay. So this is 8-hydroxyquinoline. So this one is known as the 8-hydroxyquinoline. So 8-hydroxyquinoline, if you have, and magnesium is in the +2 oxidation state, one of the ligand contains 1 negative charge, so 2 ligands, so it will be totally electrically neutral and it will precipitate out from water. So your 8-hydroxyquinoline will not be said an organic sequestering agent, because after forming the magnesium 2+ complex which is not soluble in water. Okay, so this one, water is polar, but in this case you see here it will not be soluble, and because of this reason 8-hydroxyquinoline will not be said organic sequestering agent. But if you put one, means like means substitution like SO3 minus Here just para position to this hydroxo group, then that compound whatever it has been formed will be soluble in water because it carries ultimately 2 negative charge. So obviously this will be a salt form. Let us say Na plus is there. So ultimately this compound and then Na2 is there. So that is a polar compound and it will be soluble in water. So 8 hydroxyquinoline, 5 sulfonato 8 hydroxyquinoline will be said, a organic sequestering agent, but not the 8 hydroxyquinoline. So this is the thing you have to remember. Okay. So maybe then from the next class we will enter into the isomerism and all the things of whatever I am going to cover in this coordination chemistry I have already posted in your MS Team. You can just check over there. So all these files, whatever I have just shown, let me show you. So this is the introduction. So that part is there. Naming of the coordination compound I have already posted in your MS Team. You can just find it over there exactly with the same name. And then the isomerism and CFSE, that is also posted over there. And I am just going to show, discuss this one with you details. Okay, optically active compound, which will be said simply, how easily you can just say whether it will be optically active or not. Okay, and then the last one will be the colors. So all these things. So color means. So this is my handwriting part, and only 2 pages are there. So if you want, but before that you need the crystal field stabilization, energy calculation, all other things. Okay, therefrom you can just predict many things. Like in case of the spinal structure, you can simply calculating crystal field stabilization energy. You can say whether it will prefer normal spinal or inverse spinal structure. So naming of the coordination complexes. Okay, possibly I hope that you can do it easily. Okay, the naming one. In the next class, then we will just try to follow the isomerism things and then CFSE calculations. It will take a little bit time. Okay, one more thing. Let me show you. Whatever we have in our in your practical class here. This one. Okay, the inorganic part is there. So the ferrocyan estimation and then just wait for a minute. Experiment number 2, estimation of total hardness of water sample by complexometric EDTA titration. So whenever EDTA is a better ligand than the iriochrome black tea. Iriochrome black tea is this one. Can you see? So this, sorry, this iriochrome black tea. So here SO3 minus and sodium plus. So this will be soluble in water because ultimately iriochrome black tea is going to change its color whenever it is in the protonated form and in the metal complex form. So metal complex, after chewing up all the calcium 2 plus or magnesium 2 plus, which is responsible for the hardness of water, chewing up by the EDTA, then EDTA will snatch out the metal ion present over here. So this metal ion, whenever it is metal complex form, the color is different than its protonated form. So your whenever metal complex has been formed, that should be soluble in that solution. Then only the color change you are going to expect. But if it was precipitated out, because if you do not have this SO3 minus group, okay, then it will be a non-polar compound with the magnesium 2 plus or calcium 2 plus with O minus and this O minus group. Okay, then it will precipitate out from your water solution. So then it is not going to show you the color change at the end point. So iriochrome black, this is one example where you can utilize this complexometric titration organic sequestering agent. So this ligand will be said iriochrome black tea as an organic sequestering agent. But if you do not have this SO3 minus group, then it will not be said organic sequestering agent. Okay, so that's the case.
Sir, is there any way to identify that what will be sequestering and what will be non-sequestering?
You just make a complex, okay, complex compound with that ligand, and then check whether it is water soluble or not. That should be electrically neutral totally, means with the ligand system. Okay, So if it is electrically neutral, total, and water insoluble, both the coordinations number as well as the charge of the metal ion has been balanced by the ligand. But a ligand must have some other, either anionic or cationic, centers are there, which will be responsible to make it polar so that it will be soluble in water. So that's the reason. So if it is soluble in water, then it will be said organic sequestering agent. Organic sequestering agent means organic ligand. Simply consider organic ligand. If you can make a complex of that particular organic ligand, what you expect? Most of you do not have idea, because of this reason you are saying, because whenever we synthesize any compound in our laboratory, most of the compounds are insoluble in water because we are utilizing different organic ligands. So if you utilize different organic ligands, organic compound will get dissolved in organic solvent. Okay, but that means organic solvents, polarities are also there, like the DMSO, DMF, those are polar. Chloroform, dichloromethane, those are non-polar. Acetone is, slightly polar, but more towards the non-polar in nature. Hexane, petty ether, these are totally non-polar solvent. But if you have the organic complex, most of the organic complexes are neutral in nature. So those will get soluble in organic solvent and the non-polar solvent. If your organic compound is polar in nature, like if you have the heteroatom, then you can expect some sorts of polarity or polar solvent so that it will get dissolved. Most of the coordination complexes where metal ion is there and you have a huge ligand frame, most of the complexes are insoluble in water. So if you can make a soluble, water soluble complex of that particular ligand, it will be said like the organic sequestering agent, because it can coordinate to that metal center, which will be water soluble. Okay.